Welcome all of you. First of all, thanks for joining, and welcome all of you for the first session of the Vehicle Design webinar series. My name is Veer Alakshindra, and I am a part of a math student competition team. And along with me, I have Sudhakar, Pratyay, and Himanshu. So they'll be supporting this whole event. And Sudhakar will also present some one of the demos with us. So, so before we get into some like the core part of the webinar, let me take, back to some kind of important things. So first one is that this is the whole webinar series. We have three topics. One topic is the vehicle dynamic simulation, which we'll be covering today. And then we have vehicle powertrain modeling, and the most interesting is the full vehicle simulation, where we are inviting a guest who has, in reality, built a whole vehicle model and even validate the whole vehicle model what he has built using MATLAB and Simulink. And the last one is again a very in-depth and a detailed webinar on communicating with CAN networks. So this is on 11th of November. So Sam will be joining on that day. So Sam is from our Math student competition team. And if you have not registered, so we are going to share this link in a chat. Do register for this, or maybe you can save it and feel free to join these sessions as well. So next important thing is, if you have any technical questions, maybe anything can come up. Maybe while I'm showing some kind of demos, you might have some questions regarding that. Uh, those are all technical questions, so make sure that you use the Q&A section, and while sending it, send to all the panelists so that we all can see. And then if there are some non-technical questions, for example, if you want to have some, like if the voice is not audible, or if you want me to zoom in, zoom out. And one more thing is, which is kind of interesting, is like in between when we are, presenting the content, we'll be trying to have a conversation with you. For that, again, we'll be using the chat. So when you're doing so, make sure that you're, sending it to everyone. Okay. So with this, we have a very packed agenda today, and whatever we are going to show today, and you can see that we have around 1 hour 15 minutes for the whole presentation, and then 15 minutes will be Q&A section. So we have so many topics to cover. So don't worry, whatever topics we are going to cover, we are providing an overview, and for each of these topics we have the models available. You can have, you can go through the links to the models what we are going to give you, and even a lot of uh, content will be also be having a tutorial video. So no need to worry, you have the whole, access to all the models and the videos of these examples as well. So we'll be talking about something interesting which we never used to talk about while introducing MATLAB, that is a racing line optimization. And we always used to talk about tire modeling. So this is one of the new content which we have added to this webinar series. And then Sudhakar will be talking about equation-based vehicle model. And then we'll move to longitudinal and lateral vehicle dynamics and also controls as well. And then we'll spend some good amount of time on the multi-body suspension system model, which will help you to make or build whole vehicle dynamics model using bodies, joints, and even CAD assemblies. And then we'll share some interesting resources, and then we'll have some Q&A session just to answer your queries. So with this, the first topic what we have is a racing line optimization. Now, given a track, or maybe like if you are doing some kind of lap time simulation, like a lot of students are doing it. So there are different tools, you can use those tools. Or maybe if you are in a learning phase and you want to build something from scratch at the same time learning the maths or physics behind that. This is what we are going to show today in today's this demo. So how many of you think that um, this racing line optimization, or maybe if you ask me what is racing line, it is simply optimal path through a race course. Do you think that it is important when you are doing lap time simulation? If yes, would be great if you can let us know the reason. If no, then also it's fine, no problem. So In the chat box, I mean, we have 1 minute. You can type your response or your interest, or if you worked on this earlier, you can type that in the chat box. So, I mean, we have good amount of time, 1 minute. So please go ahead. Okay. Okay, we are getting some yes, good amount of yes. Okay. 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 I mean, like extremely important. Yeah. I mean, depending on my factors. Okay. No. I mean, yeah. I mean, important to make corner fast. Okay. Okay. Fine. Fine. So the best lab. Yes. Exactly. Exactly. So the best lab. A lot of people get confused with the fact that they think that this is only for autonomous driving. No, no, it's not the case. I mean, whether it is a driver or driverless competition, you need to have that calculation. Or maybe, like, for example, if you're doing a closed loop simulation for any track, you would want the lap and as well as the velocity profile, or maybe like drive cycle. Okay. Yeah, I mean, that also makes sense, like what Apurva is telling. So Apurva is telling the race line optimization makes sense in motorsports where a driver has the width of the track to utilize. In FSA, where the width is constrained by cones, I probably wouldn't care too much about racing. I mean, I agree to some extent. Okay. Okay, fine. Okay, mixed kind of response, and a lot of you agree that it is important. A few of you have the question that, I mean, we don't need this. Okay, and that's also good. I mean, but however, the main aim over here is, I mean, an example which could be relevant to Formula student or maybe some automotive competitions, which can also give you an intro, or you can say, I mean, motivation that how MATLAB can be used for this. So given a track, for example, this kind of track, oblong test track, uh, there could be like two approaches when you are doing lap time simulation or you are trying to do some kind of tracking stuff. So first one is either you can just uh, take the center line and go through the midpoints and grab all the center points, and then you can do your further calculations. Or the other way would be that, okay, given a width and the track, let's try to, I mean, study this track, like where we can have the maximum speed, or where we can have where we have to reduce the speed, all those kind of study. For example, this is an optimized path which is based on minimum curvature. Now they are different, like there's a whole research going on this. I mean, shortest path or minimum curvature path. AI is also involved in this, but we are not going to get into all these so many, I mean, different approaches. The idea is that, okay, I mean, one is that you just take the center line, or you try to study the track, and based on certain mathematics, physics, and optimization techniques, you'll find the optimized path. Okay, so what it can do, so it has, I mean, lot of effects it can give you on your when you're performing vehicle simulations. So one is, of course, it will improve the lap time, and as an overview, I mean, as an overall idea, it will definitely improve the whole completely overall vehicle performance. Why? Because when this is not only, I would say that only the optimized path, but once you have the optimized path, the other task will be finding the velocity profile, like how, where we should accelerate, where you should decelerate. So this all, again, when you start doing that, even if you start with the point mass simulation, definitely mass, force, these all factors will come. So it has a lot of effect on different things as well. So just as a, I mean, like a simple problem statement, that okay, we have a given track of a given width, we need to find the optimized path. So we shared this project as one of our recent program called MathWorks Excellence in Innovation Program, where Jacob is from University of Waterloo. He submitted the solution. We'll talk about, I mean, this program, I mean, later, but what it did was that he used the minimum curvature approach. So what he did is that he has a track. Okay, so then he describes those track into different segments. He found the center line, and then he optimized the path. And then for the velocity, generating the velocity profile, he I mean, used the simple point mass simulation model, which is also like effective. And then he also has a lot of animations for generating GIFs and all, and PNG and images and all. And the good part is he recently, I think 3-4 days back, he came up with a nice detailed tutorial video of what work he has done, and this is also available on Git. So with this, I mean, just going through the motivation and the problem statement. And one more thing is that, I mean, we can talk a lot about this, but just, I mean, considering the time constraint, we are just giving an overview of the problem statement, and we'll go through the script what he has written. So let's switch to MATLAB. So I think most of you, I think, are aware of MATLAB window. This is how it looks like. And don't worry if you are new to MATLAB. There are different, courses through which you can go. There's an on ramp which will get you started with MATLAB. There are different tutorials as well. So we are not going to go through the basics of MATLAB. Rather, we'll try to see how the solution came up. So what Jacob did, first of all, what Jacob did. Okay, so I can see one query. I'm new here. So Ishwar, don't worry if you are new. And we all know that within 1.5 hours, you can't learn everything. We have enough resources to get you started. We have resources of, getting you started, going in depth, and even we have a series on optimization itself, so you can follow that. And there are several examples also available to download and learn yourself. Okay. So the approach what Jacob used is, first of all, he used driving scenario designer. So using driving scenario designer, you can create your track, you can generate waypoints, not the optimized one, but I mean a normal generate one. And you can make yeah, okay, so it will take a bit of time to open. Okay, so this is the driving scenario designer app, and using this you can create your track, you can generate waypoints, and if you're on the autonomous side, you can put cameras, lidar, radars, and you can generate synthetic data. I mean, a lot of things you can do, but here in case, like, you can simply, for example, uh, you can just create a road like this, and then the road features, I mean the road center, and then the road width and other information, you can export it as a MATLAB function. So this was the first step that Jacob took, and from there, close this, just give me a second. And he generated this MATLAB function. So this MATLAB function, you can see that it is having the road centers and as well as the road width. So this is just a simple example of usage of driving scenario designer, but you can do a lot of things. You can create waypoints, and as I mentioned, that you can also have different sensors to create synthetic data. So once he was done with this, then he wrote one MATLAB script, a MATLAB function, which is basically a discrete waypoint optimizer. So what he's doing is, based on the road specifications, that is the road center and road width, he wrote code for pattern search optimization, which optimized the track. Okay, so you can see over here that the inputs is the waypoint which he got from the driving scenario designer, and there are certain uh, different other parameters which is defining the optimization, and this is the whole code available over here. So we don't need to go through one by one. Okay, but this code is readily available. You can have a look into that. We'll share the link as well. And what this function is doing, that based on the road, the track and the track width, it is giving you the optimized path. So once this optimized path he got, then the next target was to get the velocity profile. So for that, again, you have this velocity profiler. Now this is I would say a very, simple approach. Because it is based on point mass simulation, which is of course like a lot of us do, and it also based on on validation. It also gives good kind of like results. So this is what Jacob also used, and he has also shared the link of the paper which he referred to. And what this is doing is that it is taking the input of the optimized path and then considering the mass, then the tangential force and the normal force, it is giving you the velocity profile. And also here certain, codes written also to get the best lap out of this. So these are the two functions. Now, these two functions, so this is all like MATLAB script. Now, to get more interactive, we also have live script. If you're not aware of that, don't worry. Just I'll give you one intro to this. So live script, using live script, you can write code, you can write equations, you can add images, and simultaneously you can also visualize the result. And then you can also convert into this different format like PDF. So, and some cool part is that you can insert different sliders, controls, and all over here. You can see drop down menus and all. Okay, so this is his final script. So over here you can see that what he's doing is he's having this text, and there are certain like initial commands just to set the whole code, and then he has put one drop down menu to get the function in place. Like for example, he has functions for oblong, and we also tested for FSG track as well, then kidney beam. And so this is the first step, setting up the track. And then there are certain bound extraction, and then finally this is his function which is calling, which he created. So you can see over here, this is the same discrete. Okay, so this is a new functionality in 21B that you can zoom in and zoom out. uh, so so this is the function what he's using. You can see that for this he has defined certain number of maximum iterations and other buffer size and other parameters as well. So this is giving him the optimized path, and later this is the velocity profile generation. So you can see that using live script you can also add some kind of drop down menus, and then you can also have edit field, like here is defining this ft max and fn max, and then his from here he's calculating the velocity profile. Okay, so I won't run it currently, it is already showing the result. Otherwise optimization will take some time because it is set to 100 optimizations. So now if we come to the result, so what we can see over here is that we have the center line, which is the dash gray color line, and then we have this colorful final best lap what he's obtained from his code. So as you can see that when it is getting the straight path, it is taking the advantage of the maximum velocity, and at the turns it is reducing the velocity, which is fair enough. I would say fair enough the results are. However, you can take the motivation from this one and add more. Like for example, you can add high fidelity vehicle model to this so that you can get more realistic results depending upon your vehicle, whichever competition you're participating in. So this is just one uh, example to show that how MATLAB can be used. Now, as a summary, it's very simple that you take the track information with width and center line. You then run an optimization by dividing this into different sections, and then you find the optimized path, and then you run the velocity profile on that based on your point mass simulation. So this is one solution. And what we have done over here is that we have also linked the resources. So yeah, so there are two solutions until now what we have obtained. Now, this is one from Jacob, and then we also have one from Arthur. So going back to that GitHub repository, so he has done a lot. More than the optimization part, it is also having the tracking control. And the good part is it is having a mid-fidelity vehicle model where he's using a dug-off tire model as well. So this also can be used as a reference for your work. Yeah. Now, you can have a look into this. Again, we have provided the link to this to the GitHub repository. And now the question comes like where this is all coming from. So just coming back to the okay, so meanwhile taking questions, so oblong, so it's just a type of track, Aditya, like kidney beam, okay, oblong, and this is just a different kind of tracks, okay. So it can, if you're working in Formula Student, you can have different tracks, FSG track or FSUK track and all. So yeah, so these are the solutions, and this is basically coming from this project, which is a part of the MathWorks Excellence and Innovation program. And if you want to register and submit your solution, feel free to do that. This is a link we are which we are again we'll share that link in the chat section. Okay, and what is this? So basically, in the MathWorks Excellence and Innovation program, we have multiple projects which are research oriented and industry oriented projects ranging from automotive, robotics, aerospace, AI. You can have, I mean, you can see there are a lot of projects over here. And based on your interest, you can register for this. And there's no time limit. Once your solution is ready, you can submit to us. We'll review the solution. And then you'll get a certificate from MathWorks that you completed this project, and even one of the most important thing which I count always, that is a LinkedIn recommendation from our MathWorks team. So, and there are others, I mean, other benefits also. Once you register for the project, you'll get an email like what else, I mean, what other benefits are there. Now, along with that, you also have, I mean, one which I really enjoy is the discussion forum. Like for example, this race line optimization project, we have a discussion. So you can see there's a huge amount of discussion going on. And even though if you don't get the direct solution to your problem, but you can see that over here, you can get a good amount of repositories and even research articles and certain YouTube videos. So it's going on and on. Yeah. So this is just a, I mean, like introduction to what it is. You can go through the web page and you can explore about. Okay. Okay, so that's a good question. So, I mean, meanwhile, we can also take some questions. Does this tool consider the characteristic of the car while optimizing the race line? For example, a car with more longitudinal acceleration will have a different racing line than one. Yes, I would say uh, um, this one. I mean, if you are looking for that kind of high fidelity model, you should check out Arthur's submission. And also, I mean, just to mention a few more. I mean, if you go to the project over here, we have also, I mean, added a good amount of references from where you can. So this is a good example of that. This is one more. A reference what we have added to the project. So you can also have a look to this, and of course, it considers all those effects which you are talking about. Okay. So with this, what we'll do is, so we'll move to the next part. Okay. So we shared all the resources what we are talking about, and now let's moving to the block diagram modeling or block diagram environment. So now, I mean, in the previous section, what we saw is we have certain equations, and then based on those equations, we are writing a code either using the built-in functions what MATLAB has, or you can build, or you are building your own function like what Jacob did. Now, another approach is, block diagram environment, which is called Simulink, where you can model your dynamic systems. So dynamic system like time-dependent systems like your automotive, aerospace, aircraft, or robots. So you can, having a set of equations and using a certain set of blocks, you can model the whole, system in a block diagram environment. And what you can do, you can model, you can simulate, you can optimize, you can analyze multi-domain systems, because all your vehicles, all your aircrafts or your robot, these are all multi-domain system consisting of thermal system, mechanical system, electrical system, pneumatic system, and many more. And then what you can do communication stuff, you can do the control part, signal processing, video and image processing. And of course, it is a platform for model-based design. So in short, you have equations, and using certain blocks which are there in Simulink, you can model your system. Now, giving an example, uh, so this is one example of a very simple, like this is for, I mean, people those who are getting started with Simulink. Yeah. If you're very much familiar of this, it's totally fine, good for you. After this, we'll move to a more advanced section or example. So this is just an, one free body diagram of a vehicle kept on an inclined surface with different forces like tractive force, rolling resistance, and the drag force. So based on this free body diagram, so this is the equation what we get. Okay, and then further, I mean, this whole equation can be converted into a model so that, I mean, you can run the model and you can do the component sizing and selection based on these equations, the model that you have built. So with this, what I'll do is, I'll give it to Sudhakar, to demonstrate you demo built in Simulink, that is the vehicle model. And then I'll come back and I'll talk about the a little bit more advanced stuffs with a vehicle model with longitudinal and lateral vehicle dynamics, and also how we are putting the driver to that so that it can properly move around, considering that it is having a double bicycle model in that. So giving it to Sudhakar. Sudhakar, let me make you as a presenter.
Thank you, Vit. Thank you for touching upon the concepts of Simulink, and primarily we can say the model-based design in Simulink. So, of course, in Simulink, model-based design is a very important tool by which we can visualize any model, and then we can find out its various issues or parameters. So, I would like to use those concepts in the upcoming demonstration. And just for our viewers, I am Sudhakar. I am an application support engineer at MathFox India. And in this demonstration, what we will see is basically how to create a vehicle system in Simulink. Due to crunch of time, I cannot create from scratch. We have a model built. We have a model which we have built it. So I will just use that model to explain various concepts. And I have already saved the various files on my desktop. I have already saved all these files. So in this case, like we talked about, that we will be talking, an electric vehicle model. So primarily we talk about battery electric vehicle model, and in short we will call it BEV, battery electric vehicle model. So first let me launch Simulink, and then I will try to show you the various models which we have designed for the battery electric vehicle. So I will launch Simulink, and just give me a second while it appears. So yeah, Simulink is now, it is getting loaded, and just give me a second. So while it is getting loaded, I will just I will start with a full blown model, but then I will talk about it, and then I will switch on to a simple model, and then follow to switching back to that full blown model. Just give me a second. Yeah. So I have this Simulink open now. I will first open the BEV model first, and then we will go on talking the other aspects of this model. So go to this. It might take a while to get loaded, so give me a few seconds. And once it appears, then we will continue with the explanation of this model. So I hope now you are able to see my screen and you are able to see a model in front of you. So, okay, give me a second. For a while. There was some directory issue. Now I have fixed it. Okay. So yeah, I will just maximize it. So I think you are able to see a battery electric vehicle model. And this is a battery electric vehicle model, as I have talked about it so many times now. So a model like this, like the one which I am showing right now on your screen, can give us a lot of detailed information, like about a motor, about a battery operation. And since in this case we are talking about a car, so we have motor and battery. Depending upon your model, you can have various other components. And here we can see that in this case we have a driver, we have motor, battery, glider. We are having various components depending upon the need of the model. And in this case, we are having driver. So basically this driver is having a reference input, and like in any control problem, we know that we have a reference input, and then we take the plant output and we compare these two. Based on that, we find out the error and we generate the controller effort. This is the basic working of any controller for that matter. So in this case, for the reference point, what we are doing is that we are not taking any constant input. Instead, we are using a standard called EPA. That stands for Environmental Protection Agency, and that is like not like a normal constant. Instead, they have set their own reference point. So we are using that reference for our model. And like we saw US06 and this EPA. So now what we can do, like what I will do is that, of course, I will run this model and I will show all these things to you. But in this model, as we see that we can have, like we can show various parameters, or we can expose the other parameters so that we can visualize how our model is doing. So in this case, we can see now I will run this model, and just to show the various plots which we have, which we can visualize. So let me just run it. It is taking a, okay, so just give me a few seconds and the plot should be up any minute now. And yeah, so these are various plots. Like I will explain all these plots once I revisit this model. But as of now, you can see that this is a plot, and yeah, okay, this is a plot of comparison of reference point and the plant output, we can say. Then we will be having some more plots which are about to appear. And okay, like, okay, I will have to drag it here. So these are various like torque, envelope, all these things we are having. So as of now, I will close these, these models, and I will start building a simple model first, like just having a glider and a driver. And then you will see how we can expand that model to include various other components, which we have just shown here. Let me close these plots for a while. I am just closing all these plots, and I will close this model as well. And then I will open a simple model, a relatively simple model, I should say. So I will go to this folder, and I will open a model which consists only of driver and a glider. So, okay, so I think it's up now. So give me a second, I will put it back. So as you can see that in this model, we are just having a driver and a glider for the sake of simplicity. Of course, an actual model will not look like this. There will be having a lot of components that we saw before. But in this case, just for the sake of simplicity, we can see that there are only two components, driver and the glider. Now, if we have a look, so we are just having a controller, like this is having a driver, but if we go, like if we click on this subsystem, and if I have a look at it, I will see that this is just a controller. And maybe, okay, so you can see that this is just a PID controller. So it is like taking some reference points, some inputs from the plant, and then giving the controller effort. This is just a controller. So like in this case, we can see that we have controller followed by the glider. These two things we are having now. Now the driver system, like as we saw before, that this is taking the EPA as the reference point and the plant output as the comparison point. So this is like calculating the error and then giving the controller effort. These things are happening here. Now what I will do is that I will just open this subsystem to show the various equations which we have used to model this particular block. So now you can see a lot of equations are there, but just to briefly touch upon the equations, like we touched upon those points. So in this case, we can see that there are various forces involved, as in aerodynamic drag, the inertial force, the grade force, rolling resistance, and so on. So now the tractive force that will basically drive the car, that has to overcome all these forces. So like you can see that this is just a balancing equation, like tractive force is balancing all of these forces. Now, if you have a look at the diagram here, so we can see that in this case, we are having a tractive force, and then this is equal to all of the other forces. Now, if we divide this force by mass, we will get acceleration, force equal to mass into acceleration, followed by, if we integrate the acceleration once, we will get velocity. Again integrated, we will get the displacement. So depending upon now, like this is just a very high level overview of the glider subsystem, which we have used it. Okay? So now we will go back to the main model. Let me click here, and I am back again. I am back to the main model. And as far as like we have already seen that we are just having a control and the glider car. So I think this is the very basic model, which can be used to visualize the car, we can say, the electric vehicle model. Now I will run it to show the performance of the model. In this case, I will just compare how the model is behaving with respect to the EPA standard. If I maximize the plot, you will see that there are two different colors in this plot, two lines, yellow line and the blue line. I hope it's visible. And if you look closely, those two lines are superimposed, completely superimposed. So in the case of control study, we can say that it's tracking the reference point very closely, means our model is doing damn good. So like yellow and blue. Yellow is the reference point which we provided, and blue is the response of my model. So our model is doing good. This we can conclude from this particular plot. I will close this plot for a while, and like we saw that model is doing good. Now I will talk about another concept called power loss model. Power loss model will be our basis of our next model, the battery electric vehicle model, where we will be having motor, battery, and so on. So power loss model basically deals with three parameters, like the name indicates, power loss. So power input, power output, and the power loss. So now we will use those three parameters to model the equations in the next model, like model as in this model, and the next model will be having the power loss equations. So without much ado, I will close this model and I will relaunch the BEV model. I will relaunch it, and I am not being at the chat, but yeah, we will look upon a few questions towards the end of this demonstration. If I open the BEV model, like I think you have already seen this before, but now I will touch upon the various blocks here. I hope it's visible to you. I will just maximize it, and it's here. So now, apart from driver and the glider, we have various components like motor, battery, and so on. We are also having a braking system, drive line. Like these are the things which are crucial to drive a car, to drive an electric vehicle for that matter. Now, in this case, we can see that if we go on to motor block, like we talked that now we are talking about power loss model. So in this case, we are having like power loss as in power input, power output, and power loss. So we are now relying on these equations to model the motor block. So you can see that we are having APP, that stands for accelerator, pedal position, and the motor speed. And based on these parameters, we are calculating the torque and so on. So similarly, we have like modeled other blocks in our this particular demonstration. So now I will again go back to the main model. I will go back to the main model. And as you can see, there is battery component also, and the motor is connected to battery. Then there are like motors connected to the drive line and so on. So the reason why motor and battery are connected is because the power input to the motor is actually the power output to the battery. So we like, this is just the things which are driving our glider, we can say that. Now the driver block, we have already seen this, but in case you have not noticed it before, like I did not open the PID block, I will do it for at this time. So if we have a look at PID block, we are just using a PI controller in fact. I will click it once, yeah. So if you have a look at it, like D part is 0. Means we are using a PI controller for controlling this battery electric vehicle model. So I will so now we have touched upon the, I should say, major blocks of this particular model, and I will leave it to you to explore the other blocks. All these files will be made available to you. And now I will run this model to show the other visualizations, like we saw the comparison of response and the reference. Now I will talk about the torque, state of charge, and so on. So like this is the, like you saw it before also, the comparison of response and the reference. And same goes for like we are having other plots like state of charge versus time, like the battery was at 95%, then at the end of the drive cycle it was at 65%. Then we have other envelopes, as in like battery power envelope, like battery powered envelope, then we have motor torque and so on. But depending upon our need or our visualization, we can add several plots to this model, and that is the beauty of Simulink. You can visualize on the go, and then accordingly you can tweak your parameters to better design your model or to come up with a better response. So I think that's all for this model. I will stop sharing the screen now.
Okay, perfect. I mean, so Sudhakar covered that concept, and again, as we mentioned, and if you're not new to MATLAB and Simulink, a lot of you have already watched this video from Ed and Christoph. So this vehicle modeling using Simulink. So again, we'll provide the link, I think, in the chat, and then you can have a look and learn more. And all the files which we just showed for the Simulink, which Sudhakar showed, I mean, those are all available on the file exchange and GitHub as well. So let's moving ahead. Now, there was a question talking about that how the XY coordinates of a track are incorporated for doing a closed loop simulation. So this is what we are going to answer. So for answer that, now the plant has to, I mean the plant which in the previous case was the vehicle longitudinal vehicle dynamics. Now you have to also include the lateral vehicle dynamics. Now again, if you want, and a lot of students have done that, if you want, you can again use the same approach, having equations like, for example, equation of bicycle model or 6D of model. These are readily available everywhere on the internet, different research papers. You can use those equations and you can model this longitudinal lateral vehicle dynamics. What we are providing is that we are providing you certain set of blocks. What type of blocks? Like which is already solving, or which is already having the built up model for 3D of longitudinal model, or single track model, or dual track model, or even 6D of model. What you need to do is that for certain inputs, maybe like wheel steering angle, longitudinal velocity, these are very simpler models. I would say this can be good for initial learning, but further you'll be incorporating the tire forces as well, which is the longitudinal lateral forces on wheels. Yeah, so such that you can get the vehicle motion in longitudinal, lateral, and yaw, and provided other information also like the tire forces, the longitudinal lateral forces, and all. So what how to uh, uh, solve or utilize these blocks? So for this we have something called as vehicle dynamics block set. The most important part on the slide is on the left side, that is library of blocks. So this uh, vehicle dynamics block set gives you access to a lot of different library of blocks like powertrain, wheels and tires, then vehicle body, which we are going to talk about today. Uh, I just saw a question, do we have a tire model? Yes, we do have a tire model. We'll talk about a tire model implementation in multi-body as well. So, and then we have vehicle scenarios and many other blocks and suspension as well. In the middle, what you see is a pre-built scenes, which is, I would say it is more relevant to the autonomous driving, which we are not going to talk about, but definitely you can check there are other resources as well. And you can also check the fully assembled reference applications, wherein you have different applications. For example, you have constant radius reference application, you have braking test reference application, wherein you have a ready to use block, ready to use model. The only thing is that you need to change the parameters as per your requirements. Yeah. So we'll be focusing on the vehicle body blocks, which are having like, which are, these are the ones like you can say vehicle body 1D of, 3D of, then 3D of, single track, dual track, and even 6D of. Now, it has certain input parameters and it has certain output parameters. The only thing what you need to make sure is that when you're using these blocks, the parameters are correct, which you have to feed in the block, and as well as connections are proper. If the connection is requiring a vector, you need to provide a signal as a vector. If it is having some kind of constant, you have to provide like that. Okay. So with this, let me move to the software demonstration, and also let you know that how you can find these blocks. So to find this, again, we'll move to Simulink. And it will open the startup page. And let's open this blank model so that we can go to the library. Yeah. Okay, it is taking a little bit of time, but no problem. I mean, the blank canvas is over here. And then in the library browser, when you go, okay, so over here, when you scroll down, you have this vehicle dynamics block set. And then over here, you can see that you have various powertrain, sensors, steering, suspension, utilities, vehicle body. Now, when you go inside this vehicle body, we have recently also added a motorcycle longitudinal model. If you are working on these two-wheelers, you can have a look into that. Or then we have this, these are the blocks which are there. Now, from here, you can find these blocks, and we also have different models for tires. For example, very basic longitudinal wheel disc brake model. Then we have 2DF tire model. Then we have a combined slip wheel 2DF model. So there are different tire models as well, depending upon your usage and fidelity of model, what you're looking into, you can use these. Okay, so we will see that how we are using the tire models in these examples. Okay, so with this, let's move to a very basic, simple model. Uh, let's move to this a model which with just a simple steering and with a proper certain connections and just, I mean, to visualize the longitudinal lateral vehicle dynamics in this. Yeah. So yeah, so this is the model, what you see. Okay, this model is very basic, just for the understanding. What it is doing, it is having this block. So this is a 3-DOF dual track block. And what it is doing, all these blocks, what you can also do is you can just go to the help, and from here you can grasp or learn like what equations we are using and what are these input and output parameters. Like for example, if I go to the port, okay, so for the port over here, you need to understand that okay, it's a vector, how you have to feed that. Okay, I mean, what type of array it is. For dual, if you're selecting single, this input port will be scalar. So all these information can be read through the documentation. So now what we are doing over here is that we are using a kinematic steering. Then we are using a subsystem just to, I mean, make it a array of input signals, which are the wheel angles. And then we have a steering angle over here, and we are just if I keep side by side. And yeah, one more important thing, which is we keep on getting the queries, you will see a visualization plot now running along with the simulation. So this is not a part of vehicle dynamics block set. This we have built using certain reference applications. However, if you want to access this, this is available. You can just go through the reference applications, or there are other repositories also for vehicle part tracking applications where we have added this block. So you can copy from there and just paste in your model and it will work. Okay. So let me keep this side by side. That is compiling because I restarted my MATLAB and it is taking a little bit time. Okay. Yeah, so it is over here. So you can see over here that it is giving you, and based on your steering angle, you can see that what's the vehicle motion, right? Okay. So don't worry, I mean, slowly we'll move to a high fidelity model. This is just a basic model without any tire dynamics. Okay. So now I'll stop it over here and let's go to a more, the model which is having the tire. So what I will do is, we'll move to the next model. I mean, just a quick answer to one of the questions is, are all of these features available under the academic use license? Yes, these are all available in the academic use license. Okay, now you can see that there are some more added stuffs. It has steering, same steering. It has this vehicle body, a very simplified powertrain, which is based on certain equations. And then we have a tire model, wherein we are just using the longitudinal wheel tire model, which is again a very low fidelity kind of model. And that's why if you get into this block, you can see over here that it has certain extra parameters, which are FWF and FWR, which is just taking the external longitudinal forces. Okay, so again, this also does the same thing. For a given steering and acceleration, deceleration, we are just, we can visualize how, the vehicle is moving in different directions. Okay, so this is one addition to this model. Now what we'll do is, we will answer one of the questions which was asked, a good question, that how these tracks parameters can be fed to a closed loop simulation model where we have the driver. Okay, so what we'll do is, now we'll use the same block. However, we'll have a more high fidelity tire model, and in that we'll place a driver. Okay, so before that, just a quick intro to what kind of driver model we are using or showing you over here. As coming from, it's a, I would say, lateral driver, or you can say geometric, driver, which is called Stanley controller. Okay, you must, I mean, they are different. There's Pure Pursuit, there's Stanley, then you have MPC also. A lot of people are using MPC as well. So we are just focusing on this driver implementation, which is called Stanley controller, and it was first introduced in the DARPA challenge by the Stanford Racing team. And to learn more about this, we have provided the link to this. You can learn. And however, the important thing is how we are implementing that in the Simulink model. Okay, so what it does basically, it computes the wheel steering angle, which is the major concern when you need to control the track. Okay, you need to, I mean, track a certain path or trajectory. So this is what it is doing based on certain equations, which are these equations, or you can say that based on the cross track error, it is giving you the steering angle. Okay. So again, we're not going in depth to this. We have in the nice good papers available, but the summary is that having a vehicle model and having a reference track, we are implementing one driver which is based on Stanley controller, which is giving you the steering angle based on cross-track error. Okay. So let's see the model. So, and this is quite interesting because this model has a lot of additional, I mean, visualizations which are relevant to a lot of automotive competitions. So let me open this. Okay, there are the questions asking regarding that, where can we get the models and the file exchange reference examples. See, whatever we are showing today, these all models are available. Each and every one, each and every models are available. So don't worry, we'll share the link to, I mean, once this session is over, within 4 to 5 business days, you'll get an email with all the resources. So just be relaxed. Okay. Yeah. So now this is the model. And now you can see that this is having a driver. This is having a oval track reference over here, which is actually again XY, which is the answer to one of the queries. And then it is having an environment and a passenger vehicle. Okay. Now, if I get into this, it's the same thing again. However, now instead of selecting the option for external longitudinal forces, we have option for external forces, means front and rear, both Fx and Fy forces we are considering. From where it will come? So it will come from the tire model. Now getting back into the tire model, and over here you can see that this is the tire model, and now we are having a detailed tire model. So this is how we implement it. Okay, so we are using this block. Based on this block, we are, we are having certain outputs, Fx, Fy, and moments which we are not using currently because it's a 3-DOF vehicle model. If had it been 6-DOF, we would have to use this moments. And then we are further having a driver. Now I think everyone understood like what additional things we have added to this model. Okay, and then further we have this driver model. Now, okay. So this driver model, what it has is that, again, this you can, this is available in the vehicle dynamics block set, and you have different drivers. For example, if I click on this block, you can see over here that it has longitudinal controller type. You can select based on predictive or PI, like for example, what was shown earlier in the longitudinal vehicle model where we were using PI, or you can also use a predictive driver. And then for the lateral control, basically for the steering control, what we are doing is we are having the Stanley controller. And what it needs all these parameters. Those are, certain control parameters which you need to define. And from the vehicle parameters, you need to define all these like mass and distance from your forward location of tire and rearward location of tires and all. Okay. Okay. I hope this is now like clear, like how we are making a full closed loop model. And then this is the block uh, a subsystem where we are defining the reference pose. Of course, this is not an optimal one, but you can consider it to be like we're providing the XY, we are providing the pose to this. We have the XY and theta as well. So now let me run this, and one interesting thing we'll show you. I think that's really, interesting for a lot of competition teams who are participating and former students. Meanwhile, it is running. There's a question, nice question again. Is it useful for robotics design? See, not exactly this. This is a very high fidelity, and robotics, in robotics we don't move the vehicle at very high velocity, and so that's why we are not concerned about the tire effects and all. Rather, you can use the robotic system toolbox where we have provided a simple bicycle model. But however, from here, if you want to use, you can use the 3DOF single track block model. You can use that. Okay. Can this block be used for mobile robot simulation? Yeah, I mean those vehicle block definitely it can be used for. It depends like what kind of robot you are making. If it is just a mobile robot with a normal like not crossing more than what do you say 10 meter per second, I think there's no sense of like making it very high fidelity model. So over here you can see that what you can visualize in the plot is velocity, engine RPM, and gear, and as well as the GG plotter over here. So we have also added our GG plotter visualization plotter over here. So if you're modeling it, you can also leverage these kind of visualizations to visualize your GG plot. Okay, and this is very much, studied in Formula Student competitions. Okay. So this is how, and you can see that the driver is perfectly tracking it. It's tracking each of the waypoints, and if we zoom it a bit, so this is the one. But of course, there's uh, I mean, I won't say limitation, but I mean, relating it to the optimized path, this is not taking the optimized path, but of course, we can leverage that code and find the optimized path, and that we can feed as X, Y, and theta values or define the pose, and then we can run the simulation. Okay. So this is all about, I would say, like Simulink and using based on equations. And again, resources, we have a complete tutorial on this, and we have models linked to this. Not the first one, but uh, the second one, we have the models link where you can download it, and then you can also get the access to a lot of blogs which we have made using reference applications. So you can have a look again to this. So we'll share these resources again in the chat, and when we are sending the email with all the resources. Okay. So now, what we saw until now is all equations, okay, and Simulink, which is where we were using all the one-directional signals, okay, and where we needed equations, and even like what we saw in the vehicle dynamics blocks. Once you go inside this, inside each of the blocks, you can see that all those equations are converted into a block and made a whole system for particular tires or vehicle body. Okay, now there are a lot of other engineers or other student teams, those who consider to do multi-body vehicle simulation. So now we'll move to that. I mean, going into the multi-body aspect, like if you have to perform these kind of, multi-body simulation for complete vehicle dynamics or high fidelity vehicle dynamics model, then how do you do that? So taking an example, so moving ahead, let me, one second. Think just give me a second. I think it's stuck somewhere. Okay. Yeah. Okay. So giving an example is that this is a suspension system. Okay, where this is having like hard points shown in red colors, and then you have this upper arm, lower arm, and cylinder piston mechanism. Now, to model this using multi-body, in general, you need to follow certain steps. First of all, this is, I mean, since this is not only modeling, it is basically dynamic simulation, which is taking physics into account. So definitely, for example, if you have to measure that how far the vehicle moved from certain frame of reference. So that's why it is over here very important that how you define the location or position and orientation of any of these bodies. So just to give an example, what we'll do is we will to, define how to define this using the tool what we are going to discuss. I'm just taking an example of defining hard point coordinates. Then how to build bodies, and then define motion, because motion is important, how you define motion. And the most important thing is that, okay, you build something, some multi-body, but one option is that, okay, you just give certain force, and based on the mechanism you can give torque, and then you simulate it and calculate the velocity, acceleration, angular velocity, and other in physical parameters. However, if you want to add more and more physics and make your model more, of high fidelity, for example, the suspension when you're making the piston cylinder, you can add the forces and make this piston move. But how about that taking real physics into consideration, where the mass spring damper is modeled using this damper and spring? Okay, this also we'll cover today. So moving ahead with this, so how we model this is using something called as a tool called Simscape Multibody, wherein you can build 3D mechanical systems using bodies, joints, constraints, and also, if you have CAD assemblies, that also you can import and model it. Or if you have CAD parts like a steel file, that also you can leverage, provided that you have, like a proper parameters like mass and inertia and all these parameters. Okay, then you can do that. Also, like for example, here this is just an example of piston cylinder mechanism. Okay, so in short, again, what we will do is we'll see that how using solid blocks, how using different blocks which can define the rotation and translation and even constraints and forces, we can model a multi-body system. So as an example, the suspension system. Okay. So as an example again, if I close the Simulink library browser, okay, not a problem. Where can you find all this is in the library browser. When you go, you can go to the Simscape multibody over here, and in the multibody you will see that there are different sections, belts and cables, which are not required for you. And maybe you can go to joints, because when you're defining the motion between two bodies, you need to see that, okay, what kind of joints is giving, maybe like prismatic joint, maybe like revolute for rotation, or maybe spherical joint. So this you can find it over here. And then you can have gears and couplings over here like this. And then you also can take advantage of the body elements. For example, there are different bodies. If you want to create cylindrical solid, you can create brick body. And I think the most useful is the file solid, because you might be having certain kind of parts which you want to import or include in the model. So for that, you can use this file solid. When you open this, okay, so I think I opened something. Just give me a second. Yeah. So, similarly, there are other blocks as well. Now as we move to see the model, you will understand like what we're talking about. So let's go to the model. So after this, what we'll do is, once we have, given an overview of suspension system, then we'll move to how to make a tire contact with the surface, with the road surface in multi-body. So yeah, I was talking about defining the coordinates. Okay, like where are the hard points placed with respect to a world, or fixed reference. So consider this to be a fixed reference, maybe world frame of reference. And then this is the one of the hard points, which are just denoted for the visualization with red colors. And we are not defining any inertia or density where you can see we have kept it 0. How do we define that? For that, we have something called as rigid transform. So that is what we are using. So if I click on this, the rigid transform, and okay, this is the block. And if you double click on this, you can see that what it is it requires the rotation. Like maybe you can define it based on aligned axis, standard axis, Or the best way is that if you define the rotational matrix. And the translation, again, you can define into different ways. For example, standard axis, or you can define in Cartesian. For example, how far is this hard point for a fixed frame of reference? So that you can define, and how much, like, orientation doesn't matter in this application, but yeah, you can also define that. So this all block, what you see is that these mostly all these are basically making sure that the where we want to place the hard points, they are placed, I mean, as per the dimension. So this is what we are making sure. Okay, so I mean, we just answered that how you can define the coordinate systems. Moving ahead, defining the bodies. For example, if you go to the upper arm, what you need to do is very simple. Like, you just need to bring the cylindrical block over here, and you need to define the radius and the length, and along with that, the inertia. Or I mean, here we are defining the mass. Yeah. So you define the bodies like this. However, you can also define a part. For example, I was talking about this part. Let me open um, body elements, and you can see over here that, for example, this file solid. Okay, so here over here you can import the from file, which kind of file you have, STL or something like that. You can just put it over here and make sure that it's in the current directory, and it will read that file. Okay. Then once done, now defining the motion. Now if I run this simulation, and even earlier in the slides also you saw that we have a, motion between uh, linear kind of motion between the piston and cylinder. Or maybe if I can just focus on one image, so you can see over here this one. Okay, now how to define this motion? For this, here comes the play of all those joints which we just saw in the library browser. So for example, in the shock absorber, if I go inside, these two blocks are ensuring that, okay, with the solid uh, um, bodies we have built the cylinder and piston. And how we are defining the motion, we are defining the motion using this prismatic joint. Over here you can see that the input is force and the output is velocity. I'll come back to this, like what it is all about. Okay, so we have defined the coordinates, we have defined the bodies or built the bodies, and we have also defined the motion. Now the next step is that, for example, in here, the option could be like you remove all these connections, and you can simply put a constant or signal just to feed the forces. However, we have not done that. We have added more physics to that, wherein we have defined this using a one-dimensional physics-based model, which is built using Simscape. Okay, so now what is Simscape, and a lot of things we'll also cover in detail with respect to the powertrain modeling in the next session. But just to give an overview, so Simscape enables you to build physical systems. Now, what are these physical systems? For example, your thermal system, your electrical system, your mechanical system, your fluid system. These are all physical systems. And if you combine all, this will become your multi-domain system. And something that you can see, what you can feel, those are all your physical system based on physics. Now, how do you model that? In Simscape, it enables, as I mentioned, that it enables you to build physical system. So you have certain blocks, okay, and where equations are already defined, and you need to replicate the physical network, I mean, to that, or you can say the physical block diagram of any system. For example, in here you can see the motor, which can be defined as in terms of different elements like resistor, inductors, and electromechanical converter, and then you have this mass and inertia. Okay, so this can be replicated in this form using some physical blocks which are connected by physical signals which are carrying physics. That's why, since it is based on completely physics, these are all bidirectional signals. These are not like unidirectional like Simulink what we saw. Okay, so there are like a lot of things we'll touch more base and get into deep more when we move to the, I mean, when we go to the next session, which is scheduled on 3rd of November. But just giving an idea that you can make physical model physical system and model and simulate physical systems. Okay, so that's what we have done. What we have done is we have utilized that, and in here we have connected this block to a physical network, which you can see is defined by this spring and a damper. So over here you can see if you go inside this. So this is defined by spring. You can see these springs. Okay, these are all SimScape signals. We'll talk about more in the upcoming webinar. And then we have this damper again, which is a physical system which is again built using SimScape. Yeah. And one change, you will also see that this is not showing any arrows because this is all like based on physics, and these are all carrying some kind of energy. There's energy transfer going on. Okay, so that's why these are all bidirectional signals. Yeah. So yeah, so this is how we have built the whole model. We started with defining the coordinates, we defined the bodies, we defined the motion, and then we connected this to a physical network. Yeah. So this is how the model looks like. I mean, we just played the model, and you can, these are all available. You can have a look into that. We'll share the resources again, and you can, using this is just a quarter car model. You can build a whole vehicle model using this suspension. Yeah. And then you can also study all those output forces which are needed for optimizing your suspension system. Now, talking about this, moving to the next, I mean, interesting topic, which is like how to make or how to do uh, vehicle simulation, vehicle dynamic simulation, considering the tire parameter. So for that, uh, 21B, with 21B, we have released one tire block, okay, which makes sure that it is having a, which you'll be using in the multi-body, wherein there are two ports. F will take care of, which is the follower frame, which will take care of connection to the tire, and the B, the base frame, which will take care of the contact with the infinite plane. Okay, so this, if you want to use this, you have to, I mean, install 21B because this is a recent addition to the toolbox. Okay. So again, I mean, you can see there are a lot of information over here, but the main summary of this is that using this block, you can implement the tire model in your multi-body simulation. And one requirement which is coming from the industry requirement is that you need to have the tire file in TIR format. So for example, if you're having some kind of raw tire data, which I think the tire consortium gives to the Formula student teams, you need to convert that into TIR format, and there are different tools for that as well. I mean, which you can use, and then that TIR format can be fed into this block, and then you can run the simulation. Okay, for example, just quickly going through that. Can we? Okay, so over here you can see that this is the vehicle model. Now, instead of only the suspension system, it is also having a tire model. So let me run this, and you should be able to see this in this view. Yeah. Yeah. So how we made the connections over here. So you can see over here that if you just go to this tire block, this is the tire block. This is connected to the tire geometry, and this is connected to the surface, that is, which we have defined as an infinite plane. And if I double click on this, these are the certain parameters which you need to define. So here we have defined, we have this tire underscore PARAM. However, make sure that for realistic results, when you're performing these kind of simulations, you have a proper tire, data. Okay. So with this, we have covered all these, like all the important topics, and just wanted to let you know that if you're looking for very high fidelity models or reference applications in, I mean, using multi-body, go check out this resource, SimScape Vehicle Template. It has also certain models for Formula Student Car as well with that suspension. Okay, which we coordinated, which the team worked with one of the student teams. So you can have a look into that. And we also took the quarter car model from this SimScape Vehicle Template. So again, the resources are there. You can copy, make it as a bookmark, or don't worry, we'll be sending out it all. Okay. So yeah, so with this, what we'll do is, there are certain, I mean, I think these, since we have, I mean only a few minutes remaining, better we'll take some, we'll start the Q&A session. And these are certain resources. For you, the most relevant one will be physical modeling over here, because if you're new to Simscape, it starts from scratch. From Simscape moving to Simscape multiboards. This is a good starting point if you want to have a look into this. Okay. And then to get more motivated that how the teams are using in automotive, in robotics and aerospace, you can have a look into this winner circle page. We recently, I think we also added the German winning team, Islingam, who won in the conversion category. So you can, if you go to the page, you can see that how the teams are using the tool for this application. Oh, okay, it's not opening. Maybe let me try once more. Okay, you can see over here that we are featuring these winning teams over here. And then we have, a big community based on automotive, which is called Racing Launch. And then we also have a community which is based on robotics. So if you want to join and want to get access to our recent or latest or even like relevant resources, videos, tutorials, articles, feel free to join this group. And we also already mentioned that we have a good amount of video tutorials to guide you. And we also um, have a student lounge blog where we publish technical articles from math workers, as well as we are also collaborating with different team members or faculties or students, those who have worked in this field and want to share their work to the whole community. Okay, so this is our contact address. If you have queries regarding anything, reach out to us at racinglaunch@mathworks.com. Okay, and we have also provided links to the student tutorials and videos. And going to the next session, do join this, because we'll be showing some exciting realistic models, a full vehicle, high fidelity models consisting of vehicle dynamics, then your powertrain, then your driver, everything will be there in this model where Krishna will be presenting this content. Okay, and this is again the same link which we have provided if you haven't registered for the upcoming sessions. And we'll also we'll have a live demo on one uh, simple electric vehicle model with thermal cooling. That also will touch base on the next session. And yeah, this is, a survey which we want you to fill up. Do fill this form, because this gives us a good idea that where the teams are focusing or what kind of videos we want to make. So this will help us as well as the whole community to answer a lot of questions which we haven't answered yet on our video channels and blog pages.